What if everything we think we know about the universe is just the tip of the iceberg? Imagine a cosmic puzzle so vast and intricate that even the brightest minds on Earth are still piecing it together. Hidden in the shadows of space, there are particles mysterious, elusive, and utterly fascinating that could rewrite the rules of reality as we know it. Welcome to a journey through the unknown, where we'll explore 30 mind-bending theories about the universe's hidden particles, from dark matter and dark energy to particles that might exist in dimensions we can't even perceive. This video is your ticket to the cutting edge of cosmic discovery. So buckle up and get ready to dive into the secrets of the cosmos. By the end of this video, you'll not only understand these theories but also see the universe in a whole new light. Let's begin. Now let's dive into the first theory, and it's a big one: dark matter. Imagine looking up at the night sky and realizing that everything you see, stars, galaxies, even the light itself, makes up less than 5% of the universe. The rest, that's where dark matter comes in. It's this invisible, mysterious substance that doesn't emit, absorb, or reflect light, making it impossible to see directly. But just because we can't see it doesn't mean it's not there. In fact, dark matter is everywhere, weaving through the cosmos like an invisible web. So, what does dark matter actually do? Well, it's all about gravity. Dark matter's gravitational pull is so strong that it holds entire galaxies together. Without it, stars would fly apart, and the universe as we know it wouldn't exist. But here's the catch: dark matter doesn't interact with light or ordinary matter in any other way. It's like a ghostly hand shaping the universe but leaving no fingerprints. Now you might be wondering, how do we even know dark matter exists if we can't see it? Scientists have clever ways of detecting its presence indirectly. For example, they observe how galaxies rotate. The outer edges of galaxies spin much faster than they should if only visible matter were holding them together. This tells us there's something extra, something invisible providing the extra gravitational pull. Another clue comes from something called gravitational lensing, where the gravity of massive objects like galaxy clusters bends the light from objects behind them. The amount of bending suggests there's more mass there than we can see, and that extra mass, you guessed it, dark matter. Despite all these clues, dark matter remains one of the universe's greatest mysteries. We know it's out there, shaping the cosmos, but we still don't know what it's made of. Is it a particle, a new kind of physics we haven't discovered yet? The search for answers continues, and every discovery brings us closer to unraveling this cosmic enigma. So, as we move forward, keep this in mind: dark matter isn't just a theory. It's a fundamental part of the universe, and understanding it could change everything we know about reality. Now, shifting our focus from the invisible web of dark matter, let's turn our attention to something even more mysterious: dark energy. If dark matter is the ghostly hand holding galaxies together, dark energy is the unseen force pushing the universe apart. And here's the kicker: it's doing so at an accelerating rate. So, what exactly is dark energy? Unlike dark matter, which pulls things together with gravity, dark energy seems to work in the opposite direction. It's a kind of energy that permeates all of space, and it's causing the universe to expand faster and faster over time. Think of it like this: if the universe were a balloon, dark energy would be the air being pumped into it, stretching it out at an ever-increasing speed. But why does this matter? Well, dark energy makes up about 68% of the universe's total energy content. That's more than double the amount attributed to dark matter. And while dark matter shapes the structure of galaxies and clusters, dark energy is shaping the fate of the entire cosmos. Here's where it gets even more fascinating. Scientists first discovered dark energy in the late 1990s when they were studying distant supernova. They expected to find that the expansion of the universe was slowing down due to gravity. Instead, they found the opposite: the universe was speeding up. This discovery was so groundbreaking that it earned the researchers the Nobel Prize in Physics in 2011. Now, you might be wondering, how does dark energy contrast with dark matter? While dark matter is all about gravity and pulling things together, dark energy is about repulsion and pushing things apart. Dark matter is clumpy, gathering in halos around galaxies, while dark energy is smooth and evenly distributed throughout space. Together, these two invisible forces are like the yin and yang of the cosmos, one holding it together, the other driving it apart. But what does this mean for the future of the universe? If dark energy continues to dominate, the universe could keep expanding forever, eventually leading to what scientists call the Big Freeze. In this scenario, galaxies would drift so far apart that the universe would become a cold, dark, and lonely place. On the other hand, some theories suggest that dark energy could change over time, potentially leading to a big rip, where the expansion becomes so extreme that it tears apart galaxies, stars, and even atoms. The truth is, we're still in the early stages of understanding dark energy. Is it a property of space itself, as Einstein's cosmological constant suggests, or is it something entirely new, a force we haven't even begun to comprehend? Whatever the answer, one thing is clear: dark energy is reshaping our understanding of the universe, and its discovery has opened up a whole new frontier in cosmology. As we move forward, keep this in mind. While dark matter shapes the universe we see today, dark energy is shaping the universe of tomorrow, and unraveling its secrets could reveal not just the fate of the cosmos, but the very nature of reality itself. Now, let's pivot to another intriguing piece of the cosmic puzzle: Axions. These hypothetical particles might sound like something out of science fiction, but they're a serious contender in the quest to understand the universe's hidden particles. Axions were first proposed in the late 1970s as a solution to a perplexing problem in quantum physics known as the strong CP problem. Without diving too deep into the technical weeds, the strong CP problem is essentially a mystery about why certain interactions in the subatomic world don't behave the way we'd expect them to. Axions were introduced as a way to explain this oddity, and in doing so, they opened up a whole new realm of possibilities. But axions aren't just theoretical curiosities, they might also play a crucial role in the dark matter story. You see, axions are incredibly lightweight, electrically neutral, and interact very weakly with ordinary matter. These properties make them a prime candidate for dark matter. In fact, if axions exist, they could be floating all around us right now, completely invisible yet contributing to the gravitational glue that holds galaxies together. So, how do scientists hope to detect these elusive particles? One of the most promising approaches involves using powerful magnetic fields and ultra-sensitive detectors. Experiments like ADMX, or the Axion Dark Matter Experiment, are designed to convert axions into detectable microwave photons under the right conditions. Think of it like tuning a radio to catch a faint signal from a distant station, except in this case, the signal could reveal the presence of axions. What makes axions particularly exciting is their dual role. Not only could they solve the strong CP problem, but they might also account for a significant portion of dark matter. This makes them a kind of cosmic two-for-one deal, a single particle that could answer two of the biggest questions in modern physics. Of course, axions are still hypothetical, and their detection remains a monumental challenge, but the search is far from over. With advancements in technology and new experiments on the horizon, the hunt for axions is heating up. If they're found, it would be a game changer, not just for particle physics, but for our understanding of the universe itself. As we continue to explore the mysteries of hidden particles, axions remind us that sometimes the smallest things can have the biggest impact. And who knows, the key to unlocking the secrets of dark matter, and perhaps even the universe itself, might be hiding in these tiny, elusive particles. Now, shifting our focus to another fascinating contender in the realm of hidden particles, let's talk about WIMP weakly interacting massive particles. These particles are among the most popular candidates for dark matter, and for good reason. WIMP are thought to be heavy, slow-moving particles that interact with ordinary matter only through gravity and the weak nuclear force, one of the 4 fundamental forces of nature. This makes them incredibly elusive, but their potential to explain dark matter has kept scientists on the hunt for decades. What makes WIMP so compelling is their theoretical elegance. They fit neatly into the framework of particle physics, particularly within theories like supersymmetry, which we'll explore later. According to these theories, WIMP could have been produced in the early universe in just the right amounts to account for the dark matter we observe today. Their mass and weak interactions make them a perfect match for the gravitational effects we see in galaxies and galaxy clusters. But how do you detect something that barely interacts with anything? Scientists have devised ingenious methods to search for WIMP. One approach involves using ultra-sensitive detectors buried deep underground to shield them from cosmic rays and other background noise. These detectors are designed to catch the rare moment when a WIMP collides with an atomic nucleus, producing a tiny flash of light or heat. Experiments like LUX, Xenon, and Panda X are at the forefront of this search, pushing the boundaries of technology to detect these faint signals. Another method involves looking for indirect evidence of WIMP. When 2 WIMP collide, they could annihilate each other, producing gamma rays or other particles that we can detect. Telescopes like the Fermi Gamma Ray Space Telescope scan the skies for these telltale signs, hoping to catch a glimpse of WIMP activity in regions dense with dark matter, such as the centers of galaxies. Despite decades of searching, WIMP have yet to be found. This has led some to question whether they're the right candidate after all, but the search is far from over. Advances in detector sensitivity and new theoretical insights keep the hope alive. If WIMP are out there, their discovery would be a monumental breakthrough, shedding light not just on dark matter, but on the fundamental nature of the universe itself. As we continue our journey through the mysteries of hidden particles, WIMP remind us that the universe often hides its secrets in the most unexpected places. And while they remain elusive, the pursuit of these particles drives us closer to understanding the invisible forces that shape our cosmos. Now, let's turn our attention to a particle that might just be hiding in plain sight: sterile neutrinos. Unlike their more familiar counterparts, sterile neutrinos are a bit of a mystery. Regular neutrinos, as you might know, are ghostly particles that barely interact with matter, passing through entire planets as if they weren't even there. But sterile neutrinos take this elusiveness to a whole new level. They don't interact through any of the fundamental forces except gravity, making them even harder to detect than regular neutrinos. So what makes sterile neutrinos so intriguing? For starters, they could help solve one of the biggest puzzles in particle physics: neutrino oscillations. Regular neutrinos are known to change their flavor as they travel, switching between electron, muon, and tau neutrinos. But this behavior suggests that neutrinos have mass, which the standard model of particle physics didn't originally account for. Sterile neutrinos could be the missing piece, explaining why neutrinos oscillate and why they have such tiny masses. But that's not all. Sterile neutrinos might also play a role in the dark matter mystery. Because they don't interact with light or ordinary matter, they could be floating around the universe, contributing to the invisible mass that holds galaxies together. Some theories even suggest that sterile neutrinos could be a significant component of dark matter, especially if they're heavier than regular neutrinos. This would make them a kind of warm dark matter, bridging the gap between the lightest and heaviest dark matter candidates. Detecting sterile neutrinos, however, is no easy task. Since they don't interact through the weak nuclear force, they can't be caught in the same detectors used for regular neutrinos. Instead, scientists look for indirect evidence, such as anomalies in neutrino oscillation experiments or unexplained signals in cosmic radiation. Experiments like Mini Bueni and Ice Cube are on the hunt for these elusive particles, hoping to catch a glimpse of their subtle effects. If sterile neutrinos do exist, their discovery would be a game changer. Not only would they help us understand the strange behavior of neutrinos, but they could also provide a new perspective on dark matter and the structure of the universe. As we continue to explore the hidden particles that shape our cosmos, sterile neutrinos remind us that sometimes the most profound discoveries come from the things we can't see or even touch. And with every experiment, we're one step closer to uncovering their secrets. Now, let's shift our focus to a particle that could hold the key to understanding one of the most fundamental forces in the universe, gravitons. These hypothetical particles are thought to be the carriers of gravity, much like photons are the carriers of light. But unlike photons, which we can detect and study, gravitons remain entirely theoretical. So, what makes them so important, and why haven't we found them yet? Gravitons are central to the quest of unifying quantum mechanics and general relativity, two of the most successful but seemingly incompatible theories in physics. Quantum mechanics describes the behavior of particles at the smallest scales, while general relativity explains the force of gravity on cosmic scales. Gravitons are the missing link that could bridge these two worlds. If they exist, they would explain gravity as a quantum force, mediated by particles rather than the curvature of spacetime described by Einstein. But detecting gravitons is an enormous challenge. Gravity is incredibly weak compared to the other fundamental forces, making its hypothetical particle extremely elusive. Imagine trying to find a single whisper in a roaring stadium. That's the scale of difficulty scientists face. Gravitons, if they exist, would interact so weakly with matter that they'd pass through entire planets without leaving a trace. This makes them nearly impossible to detect with current technology. Despite these challenges, the search for gravitons continues. Scientists are exploring indirect methods, such as studying gravitational waves, ripples in spacetime caused by massive cosmic events like black hole collisions. While gravitational waves themselves don't prove the existence of gravitons, they provide a framework for understanding how gravity behaves on a quantum level. Some theories even suggest that gravitons could be detected in the distant future through ultra-sensitive experiments or by observing the universe's earliest moments. The discovery of gravitons would revolutionize our understanding of the universe. It would not only confirm gravity as a quantum force but also pave the way for a unified theory of everything, a single framework that explains all the forces of nature. As we continue to explore the hidden particles that shape our reality, gravitons stand as a tantalizing reminder of how much we still have to learn. And with every breakthrough, we inch closer to unraveling the mysteries of gravity and the cosmos itself. Now, let's turn our attention to a concept that challenges one of the most fundamental ideas in physics: magnetic monopoles. Unlike the magnets we're familiar with, which always have both a north and a south pole, magnetic monopoles are hypothetical particles that possess just one magnetic pole. Imagine a magnet that's only north or only south. It sounds impossible, right? Yet, this idea has fascinated scientists for decades, and it could reshape our understanding of the universe. The theoretical basis for magnetic monopoles comes from quantum mechanics and the quest to unify the fundamental forces of nature. In the late 19th century, James Clerk Maxwell's equations described electricity and magnetism as two sides of the same coin, but they also implied that magnetic monopoles couldn't exist. However, in the 20th century, physicist Paul Dirac proposed that if magnetic monopoles did exist, they could explain why electric charge is quantized, why it comes in discrete, indivisible units. This was a groundbreaking idea, suggesting that monopoles might be hiding in the fabric of the universe, waiting to be discovered. But why haven't we found them yet? Magnetic monopoles, if they exist, are incredibly rare and difficult to detect. They are predicted to have formed in the early universe during a phase transition when the fundamental forces separated. Some theories suggest they could be as massive as a grain of sand but carry an enormous magnetic charge. This makes them both incredibly heavy and incredibly elusive. Scientists have searched for monopoles in cosmic rays, particle colliders, and even in ancient rocks, but so far, no definitive evidence has been found. The implications of discovering magnetic monopoles would be profound. They could provide crucial insights into the unification of forces, helping us bridge the gap between electromagnetism and other fundamental forces like gravity. They might also offer clues about the early universe and the conditions that existed just after the Big Bang. Some theories even suggest that monopoles could play a role in explaining dark matter or other cosmic mysteries. While the search for magnetic monopoles continues, their existence remains one of the most intriguing possibilities in particle physics. Whether they're hiding in the depths of space or waiting to be created in a high-energy experiment, their discovery would be a monumental leap forward in our quest to understand the universe's deepest secrets. And as we explore these hidden particles, we're reminded that sometimes the most revolutionary ideas come from questioning what we think we know. Now, let's shift our focus to a theory that could revolutionize our understanding of particle physics: supersymmetry, often abbreviated as SUSY. This elegant idea proposes that every known particle in the universe has a hidden partner, a sort of cosmic twin. Think of it like a mirror world where every electron, quark, and photon has a corresponding superpartner with slightly different properties. It's a concept that not only sounds fascinating but could also hold the key to solving some of the biggest mysteries in physics. So why do scientists believe in supersymmetry? One of its most compelling features is its potential to address the hierarchy problem, a puzzle that has baffled physicists for decades. The hierarchy problem revolves around the question of why the Higgs boson, the particle responsible for giving other particles mass, is so much lighter than it should be according to our current understanding of physics. Supersymmetry offers a solution by introducing these superpartners, which could balance out the equations and explain the Higgs boson's surprisingly low mass. But that's not all. Supersymmetry also has a lot to say about dark matter. One of the leading candidates for dark matter is a hypothetical particle called the neutralino, which is predicted by SUSY. Neutralinos are thought to be stable, electrically neutral, and interact only weakly with ordinary matter, perfect traits for a dark matter particle. If supersymmetry is correct, neutralinos could be everywhere, silently shaping the structure of the universe without us even realizing it. Despite its promise, supersymmetry remains unproven. Experiments at the Large Hadron Collider and other facilities have been searching for evidence of superpartners, but so far none have been found. This has led some to question whether SUSY is just a beautiful idea or if it truly reflects the nature of reality. However, many physicists remain optimistic, believing that these particles might simply be heavier or more elusive than we initially thought. The discovery of supersymmetry would be a game changer. It wouldn't just fill in gaps in the standard model of particle physics, it would open up an entirely new realm of possibilities. From explaining dark matter to unifying the fundamental forces of nature, SUSY has the potential to reshape our understanding of the cosmos. And as we continue to search for these elusive superpartners, we're reminded that sometimes the most profound discoveries come from imagining a universe far richer and more complex than we ever thought possible. Now, let's take a step into a realm that stretches the boundaries of our imagination: extra dimensions. While we're all familiar with the three spatial dimensions we experience every day: length, width, and height, some theories suggest there could be more dimensions hidden from our perception. These extra dimensions aren't just science fiction, they're a serious area of study in physics, offering potential explanations for some of the universe's deepest mysteries. So, what exactly are these extra dimensions? Imagine our universe as a sheet of paper. We can move left and right, forward and backward, and up and down. That's our three-dimensional world. But what if there were tiny, curled-up dimensions too small for us to see, existing at every point in space? This idea, rooted in string theory, proposes that particles and forces we observe might actually be influenced by interactions in these hidden dimensions. It's like discovering that the flat sheet of paper has a hidden texture we never noticed. One of the most intriguing possibilities is that hidden particles, like those we've been discussing, could exist in these extra dimensions. For example, gravity, which is much weaker than the other fundamental forces, might appear weak to us because it's leaking into these additional dimensions. This could explain why gravity doesn't fit neatly into the standard model of particle physics. Similarly, dark matter might be a particle that interacts primarily in these hidden dimensions, making it nearly invisible to our current detection methods. The implications of extra dimensions go beyond just explaining gravity or dark matter. They could also provide a framework for unifying all the fundamental forces of nature. In string theory, for instance, particles aren't just tiny points but tiny vibrating strings, and the way they vibrate depends on the geometry of these extra dimensions. This could be the key to reconciling quantum mechanics and general relativity, two theories that currently don't play well together. Of course, the idea of extra dimensions raises plenty of questions. How many dimensions are there, why are they hidden, and how can we detect them? While we don't have definitive answers yet, experiments like those at the Large Hadron Collider are searching for clues. For example, if extra dimensions exist, high-energy collisions might produce particles that briefly escape into these dimensions, leaving behind telltale signs in the data. The concept of extra dimensions challenges us to rethink our understanding of reality. It's a reminder that the universe might be far more complex and layered than we can perceive. And as we continue to explore these ideas, we're not just uncovering hidden particles, we're uncovering hidden layers of the cosmos itself. Next, we'll dive into another fascinating theory that takes us even deeper into the fabric of spacetime, quantum foam. Now, let's zoom in even further down to the very fabric of spacetime itself. At the tiniest scales imaginable, the smooth, continuous universe we know begins to break down into something far more chaotic and unpredictable. This is where we encounter the mind-bending concept of quantum foam. Picture spacetime not as a flat, serene surface, but as a bubbling, frothy sea, constantly churning with fluctuations at the smallest possible scales. This is quantum foam, the turbulent foundation of reality itself. Quantum foam arises from the principles of quantum mechanics, which tell us that at the smallest levels, nothing is ever truly still. Even empty space is alive with energy, with particles and antiparticles popping in and out of existence in a frenzied dance. These fleeting fluctuations create a kind of foam that makes spacetime appear jagged and irregular when viewed up close. It's as if the universe has a hidden texture, one that's only visible when we look at it through the lens of quantum physics. But what does this have to do with hidden particles? Well, some theories suggest that quantum foam could be the birthplace of particles we've yet to discover. In this chaotic, ever-changing environment, particles might emerge spontaneously, only to vanish just as quickly. These particles could be the key to understanding phenomena like dark matter or dark energy, as they might interact with the universe in ways we can't yet detect. Imagine a hidden world of particles flickering in and out of existence, leaving behind only faint traces of their presence. One of the most fascinating aspects of quantum foam is how it challenges our understanding of spacetime. In this realm, the very concepts of distance and time become fuzzy, as the fabric of reality itself is constantly shifting. This has profound implications for our search for hidden particles, as it suggests that the rules governing their behavior might be entirely different from those we're familiar with. For instance, particles emerging from quantum foam might not follow the same laws of physics that apply in our larger, more stable universe. Detecting these particles is no easy task, though. Because quantum foam operates at such incredibly small scales, it's far beyond the reach of our current technology. However, scientists are exploring indirect methods to uncover its secrets. For example, by studying the behavior of particles at extremely high energies, we might catch glimpses of how quantum foam influences their interactions. It's like trying to understand the ripples on the surface of a pond to infer what's happening deep below. Quantum foam reminds us that the universe is far stranger and more dynamic than it appears. It's a realm where the rules of physics as we know them break down, and where hidden particles might be waiting to reveal themselves. As we continue to probe the mysteries of quantum foam, we're not just exploring the smallest scales of existence, we're uncovering the very building blocks of reality. Next, we'll turn our attention to another intriguing candidate for dark matter, neutralinos. Now, shifting our focus to another fascinating contender in the search for dark matter, we arrive at neutralinos. These hypothetical particles are a key prediction of supersymmetry, a theory that proposes a profound symmetry between the fundamental particles we know and their yet-to-be-discovered counterparts. Neutralinos are thought to be among the lightest and most stable of these supersymmetric particles, making them a prime candidate for dark matter. So, what exactly are neutralinos? In the framework of supersymmetry, every particle in the standard model has a superpartner with slightly different properties. Neutralinos are a mix of these superpartners, specifically combining the partners of the photon, the Z boson, and the Higgs boson. This unique blend gives them some intriguing characteristics. For one, they're electrically neutral, meaning they don't interact with light or electromagnetic fields, which makes them incredibly difficult to detect. They're also massive, much heavier than most known particles, which aligns with what we expect from dark matter. One of the most compelling reasons scientists are so interested in neutralinos is their potential to explain dark matter. If neutralinos exist, they would have been produced in the early universe and could still be floating around today, forming the invisible scaffolding that holds galaxies together. Their stability and weak interactions with ordinary matter make them an ideal fit for the dark matter puzzle. Plus, their predicted properties could help solve other mysteries in physics, such as why the Higgs boson is so much lighter than expected. But how do we go about detecting something that's invisible and barely interacts with anything? Scientists have devised several clever methods to hunt for neutralinos. One approach involves looking for the faint signals they might leave behind when they occasionally collide with atomic nuclei in deep underground detectors. These collisions would produce tiny flashes of light or heat, which sensitive instruments could pick up. Another method involves searching for the byproducts of neutralino annihilations in space. If two neutralinos were to collide and destroy each other, they could produce gamma rays or other high-energy particles that telescopes could detect. Despite decades of searching, neutralinos have yet to be found. This doesn't mean they don't exist, it just means they're incredibly elusive. The search for neutralinos is a testament to the ingenuity and persistence of scientists who continue to refine their methods and build ever more sensitive detectors. It's a reminder that uncovering the secrets of the universe often requires patience, creativity, and a willingness to explore the unknown. As we delve deeper into the mysteries of dark matter, neutralinos remain one of the most promising leads. They embody the tantalizing possibility that the answers to some of the universe's biggest questions might lie just beyond our current reach. Next, we'll explore another intriguing theory that takes us into the realm of extra dimensions, Kaluza-Klein particles. Now, let's venture into a theory that stretches the boundaries of our understanding of space itself, Kaluza-Klein particles. These hypothetical particles emerge from the idea that our universe might have more than the three spatial dimensions we're familiar with. Imagine for a moment that there are hidden dimensions, tiny, curled-up spaces too small for us to perceive directly. Kaluza-Klein particles are thought to be vibrations or excitations within these extra dimensions, and they could hold the key to some of the universe's most perplexing mysteries. The concept of extra dimensions isn't just science fiction, it's a serious proposal in theoretical physics. In the early 20th century, physicists Theodore Kaluza and Klein suggested that if we add a fourth spatial dimension to Einstein's theory of general relativity, we can unify gravity and electromagnetism. While their original idea didn't fully pan out, it laid the groundwork for modern theories like string theory, which posits that the universe could have up to 10 or even 11 dimensions. Kaluza-Klein particles are a natural consequence of these theories, representing the way particles might behave if they could move through these hidden dimensions. So, what makes Kaluza-Klein particles so intriguing? For one, they could help explain dark matter. If these particles exist, they would be massive and interact very weakly with ordinary matter, making them nearly invisible, just like dark matter. In fact, some versions of the theory suggest that the lightest Kaluza-Klein particle could be stable and abundant enough to account for the missing mass in the universe. This would mean that dark matter isn't just made of some exotic particle we haven't discovered yet, but rather a manifestation of the hidden geometry of space itself. But the implications don't stop there. Kaluza-Klein particles could also shed light on other cosmic puzzles, such as the hierarchy problem in particle physics. This problem asks why gravity is so much weaker than the other fundamental forces. If particles can exist in extra dimensions, their properties might be diluted across these dimensions, explaining why gravity appears so feeble in our three-dimensional world. Additionally, detecting Kaluza-Klein particles could provide indirect evidence for the existence of extra dimensions, opening up a whole new realm of physics. Of course, detecting something that exists in dimensions we can't see is no easy task. Scientists are exploring ways to find evidence of Kaluza-Klein particles, often by looking for their effects in high-energy particle collisions or through their gravitational influence. While no direct evidence has been found yet, the search continues, driven by the tantalizing possibility that these particles could unlock a deeper understanding of the universe. As we wrap up our exploration of Kaluza-Klein particles, we're reminded once again that the universe is far stranger and more complex than we can imagine. These particles challenge us to think beyond the familiar and consider the possibility that the answers to our biggest questions might lie in dimensions we can't even see. Next, we'll turn our attention to another fascinating theory, mirror matter, a concept that suggests the existence of a hidden, parallel universe right alongside our own. Now, let's step into a world where the familiar becomes extraordinary, a world where everything we know might have a hidden twin. This is the realm of mirror matter, a fascinating theory that proposes the existence of a parallel form of matter, almost like a reflection of our own universe. Imagine a shadowy counterpart to every particle we're familiar with, existing alongside us but just out of reach. This isn't science fiction. It's a serious scientific idea that could help unravel some of the universe's deepest mysteries. Mirror matter is thought to be a hypothetical form of matter that mirrors the properties of ordinary matter, but interacts with it only very weakly, if at all. In this theory, every particle we know, electrons, protons, neutrons, could have a mirror counterpart. These mirror particles would follow the same physical laws as their ordinary counterparts, but would exist in a kind of parallel reality, invisible to us except through their gravitational effects. This makes mirror matter a compelling candidate for dark matter, the elusive substance that makes up a significant portion of the universe's mass but doesn't interact with light. One of the most intriguing aspects of mirror matter is how it could explain the dark matter problem. If mirror particles exist, they would be massive and abundant, yet they wouldn't emit or absorb light, making them nearly impossible to detect directly. This aligns perfectly with what we know about dark matter. It exerts gravitational influence but remains invisible. Some theories even suggest that mirror matter could form its own stars, planets, and galaxies, creating a hidden universe that coexists with ours, intertwined yet separate. But how could mirror matter interact with ordinary matter? The answer lies in gravity. While mirror particles wouldn't interact with electromagnetic forces, they would still be influenced by gravity, just like ordinary matter. This means that mirror matter could clump together, forming structures that affect the gravitational fields we observe in the cosmos. For example, the gravitational lensing effects we see around massive objects like galaxy clusters could be partly due to the presence of mirror matter. The idea of mirror matter also opens up exciting possibilities for particle physics. If mirror particles exist, they could help explain certain anomalies in experiments, such as unexpected results in neutrino oscillations or particle decays. Some scientists have even proposed that mirror matter could be responsible for the mysterious signals detected in dark matter experiments, though this remains speculative. Detecting mirror matter, however, is a monumental challenge, since it doesn't interact with light or ordinary matter in any significant way. Traditional detection methods won't work. Instead, researchers are looking for subtle gravitational effects or anomalies in particle physics experiments that could hint at its existence. While no definitive evidence has been found yet, the search for mirror matter continues to inspire new experiments and theoretical models. As we explore the concept of mirror matter, we're reminded that the universe might be far more complex and interconnected than we ever imagined. This theory challenges us to consider the possibility of a hidden parallel reality, one that could hold the key to understanding dark matter and the true nature of the cosmos. Next, we'll dive into another captivating idea, primordial black holes, which could offer a completely different explanation for the universe's missing mass. Now let's shift our gaze to a different cosmic mystery, one that takes us back to the very beginnings of the universe. Imagine tiny, dense remnants from the Big Bang lurking in the shadows of space. These are primordial black holes, and they might just hold the key to solving the dark matter puzzle. Primordial black holes are thought to have formed in the first moments after the Big Bang, when the universe was a hot, dense soup of particles. Unlike the black holes we're familiar with, which form from collapsing stars, these ancient black holes could be as small as an atom or as massive as a planet. Their existence could explain why dark matter seems to be everywhere yet remains invisible. If these black holes are scattered throughout the cosmos, their gravitational pull could account for the missing mass we've been searching for. But how do we detect something so elusive? Primordial black holes don't emit light, and if they're small enough, they might not even interact with ordinary matter in noticeable ways. However, scientists have come up with clever methods to search for them. One approach involves looking for gravitational microlensing events. When a primordial black hole passes in front of a distant star, its gravity bends the star's light, causing a temporary brightening. By monitoring millions of stars, astronomers hope to catch these fleeting glimpses of hidden black holes. Another detection method relies on their potential interactions with cosmic rays or gamma rays. If a primordial black hole were to collide with a neutron star, for example, it could produce a burst of radiation that telescopes could pick up. Even more intriguing is the idea that these black holes might emit tiny amounts of radiation through a process called Hawking radiation, though this would be incredibly faint and difficult to observe. The implications of primordial black holes are profound. If they exist, they could rewrite our understanding of the early universe and the nature of dark matter. They might also help explain other cosmic mysteries, like the origins of supermassive black holes at the centers of galaxies. Some theories even suggest that primordial black holes could have seeded the formation of galaxies themselves, acting as gravitational anchors in the early cosmos. As we explore this theory, we're reminded that the universe is full of surprises. Primordial black holes challenge us to think beyond the familiar and consider the extraordinary possibilities hidden in the fabric of space and time. Next, we'll venture into the realm of particles that defy the speed of light, tachyons, and explore how they might reshape our understanding of physics. Now let's take a leap into the realm of the extraordinary, where the rules of physics as we know them are turned upside down. Enter Tachyons, hypothetical particles that, if they exist, could travel faster than the speed of light. Yes, you heard that right. These particles, first proposed in the 1960s, challenge one of the most fundamental principles of modern physics, Einstein's theory of relativity, which states that nothing with mass can exceed the speed of light. But tachyons, by their very nature, would defy this rule. The idea of tachyons comes from the mathematics of special relativity. While Einstein's equations suggest that particles with mass can't reach or surpass the speed of light, they don't explicitly forbid the existence of particles that always travel faster than light. Tachyons, if they exist, would have imaginary mass, a concept that sounds like science fiction but is rooted in theoretical physics. This imaginary mass would allow them to move at superluminal speeds, meaning they'd be faster than light from the moment they come into existence. But here's where things get tricky. If tachyons were real, they'd create some serious paradoxes. For instance, their existence could lead to violations of causality, the principle that cause must always precede effect. Imagine a tachyon traveling faster than light. From certain perspectives, it could appear to arrive at its destination before it even left its starting point. This would create a situation where an effect could seemingly happen before its cause, which throws a wrench into our understanding of time and reality. Despite these mind-bending possibilities, tachyons remain purely speculative. No experimental evidence has ever been found to support their existence, and many physicists remain skeptical. Some argue that the concept of tachyons is more of a mathematical curiosity than a physical reality. However, that hasn't stopped scientists from exploring their potential implications. In fact, tachyons have found a place in theoretical discussions about faster-than-light travel, time travel, and even the nature of the universe itself. One intriguing idea is that tachyons could be connected to dark energy, the mysterious force driving the accelerated expansion of the universe. Some theories suggest that tachyons might interact with dark energy in ways we don't yet understand, potentially offering clues about the cosmos's ultimate fate. Others have proposed that tachyons could be linked to quantum mechanics, possibly playing a role in phenomena like quantum entanglement, where particles seem to communicate instantaneously across vast distances. While tachyons remain a fascinating topic of speculation, their existence would require a complete overhaul of our current understanding of physics. For now, they serve as a reminder that the universe is full of mysteries waiting to be unraveled. As we continue our journey through the hidden particles of the cosmos, let's turn our attention to another intriguing concept, quark-gluon plasma, a state of matter that takes us back to the universe's fiery beginnings. Now, let's rewind the cosmic clock to a time when the universe was just a fraction of a second old, a time so hot and dense that even atoms couldn't exist. This is the era of quark-gluon plasma, a state of matter so extreme it defies everything we know about the ordinary world. Imagine a soup so energetic that the building blocks of protons and neutrons, quarks and gluons roamed freely, unbound by the forces that usually hold them together. This is quark-gluon plasma, and it's not just a theoretical idea. Scientists have actually recreated this primordial state in particle colliders, giving us a glimpse into the universe's fiery infancy. Quark-gluon plasma is thought to have existed just microseconds after the Big Bang, when temperatures soared to trillions of degrees. In this chaotic environment, quarks and gluons, the fundamental particles that make up protons and neutrons, were too energetic to stick together. Instead, they zipped around freely, creating a superheated, ultra-dense soup. As the universe expanded and cooled, this plasma eventually condensed into the protons and neutrons we know today, forming the first atomic nuclei. But what's truly fascinating is that this extreme state of matter might hold clues about the hidden particles that shaped the early universe. One intriguing possibility is that quark-gluon plasma could have been a breeding ground for exotic particles that no longer exist in our current universe. In such a high-energy environment, particles with unusual properties might have formed, only to disappear as the universe cooled. Some theories suggest that these particles could have played a role in the formation of dark matter, the mysterious substance that makes up most of the universe's mass. Others propose that quark-gluon plasma might have produced particles that interacted with dark energy, influencing the universe's expansion in ways we're only beginning to understand. Scientists have been studying quark-gluon plasma in experiments like those at the Large Hadron Collider, where they smash heavy ions together at nearly the speed of light. These collisions recreate the extreme conditions of the early universe, allowing researchers to observe how quarks and gluons behave in this exotic state. What they've found is that quark-gluon plasma behaves more like a perfect fluid than a gas, with almost no viscosity. This discovery has deepened our understanding of the strong nuclear force, one of the four fundamental forces of nature, and opened up new questions about the universe's origins. While quark-gluon plasma might seem like a relic of the distant past, its study has profound implications for our understanding of the cosmos. By exploring this extreme state of matter, scientists hope to uncover clues about the hidden particles that shaped the early universe and continue to influence its evolution. As we move forward in our exploration of the universe's hidden particles, let's turn our attention to another fascinating concept: Preons, the hypothetical building blocks that could explain the diversity of particles in the Standard Model. Now, shifting our focus to an even smaller scale, let's explore the intriguing idea of preons. These hypothetical particles are thought to be the building blocks of quarks and leptons, the fundamental particles that make up everything in the Standard Model of particle physics. If preons exist, they could help explain why there's such a wide variety of particles in the universe, each with unique properties and behaviors. The Standard Model has been incredibly successful in describing the particles we know, like electrons, quarks, and neutrinos, as well as the forces that govern their interactions. But one question that has puzzled scientists is why there are so many different types of particles. Why do quarks come in 6 flavors, and why do leptons have such distinct masses? Preons offer a potential answer. Imagine if all these particles weren't fundamental after all, but instead made up of even smaller, more basic components. That's the essence of the preon theory. According to this idea, quarks and leptons could be composed of preons, which would combine in different ways to create the variety of particles we observe. For example, the difference between an electron and a quark might simply come down to how their preons are arranged. This would be similar to how protons and neutrons are made of quarks, but on an even smaller scale. If preons exist, they could provide a simpler, more unified explanation for the complexity of the Standard Model. One of the most exciting aspects of preon theory is its potential to solve some of the biggest mysteries in physics. For instance, it could help explain why particles have the masses they do, or why certain particles interact in specific ways. It might even shed light on the nature of dark matter, as preons could form the basis of particles we haven't yet discovered. However, despite its promise, preon theory remains speculative. No direct evidence for preons has been found, and their existence would require a radical rethinking of our understanding of particle physics. Scientists have proposed various models to describe how preons might work, but testing these ideas is incredibly challenging. Preons, if they exist, would be far smaller than quarks and leptons, making them nearly impossible to detect with current technology. Some theories suggest that preons could be bound together by a new, unknown force, adding another layer of complexity to the puzzle. Despite these challenges, the search for preons continues, driven by the hope of uncovering a deeper layer of reality. As we ponder the possibility of preons, it's worth remembering that every new discovery in physics has started as a bold idea. From quarks to black holes, many of the universe's secrets were once hidden in plain sight, waiting for the right tools and theories to reveal them. Whether preons turn out to be real or not, their exploration pushes the boundaries of our knowledge and keeps us asking the big questions. And with that, let's turn our attention to another fascinating concept, the hidden valley theory, which proposes an entirely new sector of particles that could revolutionize our understanding of the cosmos. Now, stepping into a realm that feels almost like science fiction, let's explore the hidden valley theory. This fascinating idea suggests that there could be an entirely separate sector of particles, hidden from our current understanding of physics, interacting so weakly with ordinary matter that they've remained invisible to us until now. Think of it as a parallel universe of particles existing right alongside the ones we know, but operating under different rules. The hidden valley theory gets its name from the idea that these particles are hidden in a metaphorical valley, separated from the particles of the standard model by a large energy gap. This means they don't interact with the forces we're familiar with, like electromagnetism or the strong nuclear force, making them incredibly difficult to detect. Instead, they might interact through a new, unknown force, one that operates entirely within this hidden sector. One of the most exciting implications of this theory is its potential connection to dark matter. If dark matter is made up of particles from this hidden sector, it could explain why we've struggled to detect it directly. These particles might only interact with ordinary matter through gravity or some other extremely weak force, making them nearly invisible to our current experiments. This idea opens up a whole new avenue for understanding the mysterious substance that makes up most of the universe's mass. But the hidden valley theory doesn't stop at dark matter. It could also revolutionize our understanding of particle physics as a whole. For example, it might help explain why certain particles have the masses they do, or why some interactions seem to violate the symmetry we expect in the standard model. It could even provide clues about the nature of the Higgs boson, the particle responsible for giving other particles their mass. Scientists are already exploring ways to test this theory. One approach involves looking for rare decays of known particles, which could hint at the existence of hidden sector particles. Another involves searching for anomalies in high-energy collisions, where hidden particles might briefly reveal themselves before disappearing back into their secluded realm. While these experiments are challenging, they hold the promise of uncovering a whole new layer of reality. The hidden valley theory reminds us that the universe is far stranger and more complex than we can imagine. It challenges us to think beyond the standard model and consider the possibility of entirely new realms of physics. Whether or not this theory proves true, it pushes the boundaries of our knowledge and keeps us searching for answers to the universe's deepest mysteries. And with that, let's move on to another intriguing concept, Planck particles, which take us to the very edge of what we know about the fabric of reality. Now, let's zoom way into the smallest scales imaginable, where the fabric of reality itself becomes fuzzy and uncertain. This brings us to Planck particles, hypothetical entities that exist at the Planck scale, the tiniest possible measurements in the universe. Named after physicist Max Planck, these particles are thought to operate at distances so small that they challenge our very understanding of space and time. At the Planck scale, the rules of classical physics break down and quantum gravity takes center stage. Planck particles are believed to be the building blocks of spacetime itself, existing in a realm where gravity and quantum mechanics merge. This is where the universe's most fundamental interactions occur, and where the secrets of quantum gravity might finally be unlocked. But here's the catch: the Planck scale is unimaginably small. To give you an idea, the Planck length is about 1/trillionth of a trillionth of the size of an atom. That's so tiny that even our most advanced particle accelerators can't come close to probing it. So what makes Planck particles so special? For one, they could hold the key to unifying the two great pillars of modern physics, quantum mechanics and general relativity. While quantum mechanics explains the behavior of particles at the smallest scales, general relativity describes the force of gravity on cosmic scales. But these two theories don't play well together, and Planck particles might be the missing link that bridges the gap. They could help us understand how gravity works at the quantum level, solving one of the biggest mysteries in physics. But detecting Planck particles is no easy task, because they exist at such extreme scales. They're far beyond the reach of current technology. Even if we could build a particle accelerator the size of the Milky Way, it still wouldn't be powerful enough to probe the Planck scale. That's why scientists are exploring indirect methods, such as studying the remnants of the Big Bang, or looking for tiny ripples in space-time that might hint at the presence of these elusive particles. Another challenge is that Planck particles might not behave like the particles we're familiar with. They could exist as fleeting fluctuations in the quantum foam, the chaotic, ever-changing fabric of space-time at the smallest scales. This means they might not have a fixed mass or charge, making them even harder to detect. Yet, despite these challenges, the search for Planck particles continues, driven by the hope that they could revolutionize our understanding of the universe. Planck particles remind us that the universe is full of mysteries waiting to be uncovered. They challenge us to think beyond the limits of our current knowledge and imagine what lies at the very edge of reality. Whether or not we ever detect them, the pursuit of Planck particles pushes the boundaries of science and keeps us asking the big questions about the nature of existence. And with that, let's turn our attention to another fascinating concept, chameleon particles, which might hold the key to understanding dark energy and the accelerating expansion of the universe. Now, shifting our focus to another intriguing concept, let's explore chameleon particles, hypothetical entities that, much like their namesake, adapt their properties depending on their surroundings. These particles are theorized to change their mass and interaction strength based on the density of their environment, making them incredibly elusive and fascinating to scientists. Imagine a particle that behaves differently in the vacuum of space compared to the dense environment of a laboratory. This adaptability is what makes chameleon particles so unique and potentially groundbreaking in our understanding of the universe. One of the most compelling aspects of chameleon particles is their potential connection to dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy makes up about 68% of the universe's total energy, yet its nature remains one of the biggest puzzles in cosmology. Chameleon particles could provide a clue. Some theories suggest that these particles might interact with dark energy in ways that explain why the universe's expansion is speeding up. If true, this would offer a new framework for understanding one of the most profound mysteries in modern physics. But how do chameleon particles work? In regions of low density, such as the vast emptiness of space, these particles are thought to have a very small mass, making them nearly invisible to detection. However, in denser environments like those found on Earth or within galaxies, their mass increases and they become more detectable. This behavior allows them to hide in plain sight, blending into their surroundings and avoiding detection by conventional means. It's this chameleon-like quality that makes them so challenging to study, but also so promising as a potential explanation for dark energy. Scientists are actively searching for chameleon particles using a variety of innovative methods. One approach involves using highly sensitive laboratory experiments to detect tiny forces that could be exerted by these particles. Another method looks for their effects on the behavior of light as it travels through space, searching for subtle distortions that might hint at their presence. While no definitive evidence has been found yet, the search continues, driven by the tantalizing possibility that chameleon particles could unlock new insights into the nature of dark energy and the cosmos. What makes chameleon particles particularly exciting is their ability to bridge the gap between particle physics and cosmology. By potentially explaining dark energy, they could help us understand not just the behavior of the universe on the largest scales, but also the fundamental forces that govern it at the smallest scales. This dual role makes them a key focus of research, as they could provide a unified explanation for phenomena that currently seem unrelated. As we continue to probe the mysteries of the universe, chameleon particles remind us that the answers we seek might be hiding in plain sight, waiting for the right conditions to reveal themselves. Their elusive nature challenges us to think creatively and push the boundaries of our technology and imagination. And with that, let's turn our attention to another fascinating theory: unparticles, a concept that challenges our very understanding of what particles are and how they behave. Now, let's venture into the strange and fascinating world of unparticles, a concept that turns our traditional understanding of particles on its head. Unlike the particles we're familiar with, such as electrons or protons, unparticles don't have a definite mass. Instead, they exist in a kind of fuzzy state, behaving more like a continuous spectrum rather than discrete entities. This idea challenges the very foundation of particle physics, where mass and energy are typically well-defined properties. The concept of unparticles was first proposed to explain certain anomalies observed in particle physics experiments. These anomalies don't fit neatly into the standard model, the framework that describes the known particles and forces in the universe. Unparticles offer a potential explanation by suggesting that there's an entirely new sector of physics operating at scales we haven't yet explored. Imagine trying to measure something that doesn't have a fixed size or shape. It's like trying to catch smoke with your hands. That's the kind of challenge unparticles present to scientists. One of the most intriguing aspects of unparticles is how they interact with ordinary matter. Because they don't have a definite mass, their behavior is governed by something called scale invariance. This means their properties don't change regardless of the scale at which you observe them. It's a bit like looking at a fractal pattern. No matter how much you zoom in or out, the pattern looks the same. This unique characteristic could help explain why certain particle interactions don't follow the rules we expect, opening the door to new physics beyond the standard model. The search for unparticles is still in its early stages, but the implications of their existence are profound. If unparticles are real, they could provide insights into some of the biggest unanswered questions in physics, such as the nature of dark matter or the unification of forces. They might even help us understand why the universe behaves the way it does on both the smallest and largest scales. While they remain theoretical for now, the possibility of unparticles has sparked a wave of interest and research as scientists work to design experiments that could detect their subtle effects. As we wrap up this exploration of unparticles, it's clear that they represent a bold and imaginative step forward in our quest to understand the universe. They remind us that the answers we seek might lie in ideas that challenge our most fundamental assumptions. And with that, let's turn our attention to another groundbreaking theory: Technicolor particles, which offer a fresh perspective on how particles acquire mass. Now, shifting our focus to another intriguing concept, let's dive into the world of Technicolor particles. These hypothetical particles offer a completely different approach to understanding how particles acquire mass, challenging the widely accepted Higgs mechanism. While the Higgs boson, discovered in 2012, is celebrated for explaining mass through interactions with the Higgs field, Technicolor particles propose an alternative framework rooted in a more complex and dynamic process. Technicolor particles emerge from a theory known as Technicolor, which suggests that mass isn't granted by a single Higgs field, but instead arises from a series of interactions involving new, strongly interacting particles. Think of it like this: instead of one actor on stage delivering the performance, you have an entire ensemble working together to create the effect. In this case, the ensemble is made up of technoquarks and technogluons, particles that bind together in a way similar to how quarks and gluons form protons and neutrons. This binding process generates mass without the need for a Higgs boson, offering a fresh perspective on one of the most fundamental questions in physics. One of the most compelling aspects of Technicolor particles is their potential to address some of the limitations of the Higgs mechanism. For instance, the Higgs boson's relatively low mass has raised questions about why it isn't much heavier, a puzzle known as the hierarchy problem. Technicolor theories sidestep this issue entirely by eliminating the need for a Higgs particle, instead relying on the dynamics of these new particles to explain mass. It's like solving a puzzle by reimagining the pieces rather than forcing them to fit. But how do we detect Technicolor particles if they exist? Unlike the Higgs boson, which was discovered through collisions at the Large Hadron Collider, Technicolor particles would leave behind a more subtle signature. Scientists are looking for unusual patterns in particle collisions, such as excess energy or unexpected decay products that could hint at their presence. It's a bit like searching for a hidden message in a noisy conversation. You have to listen carefully for the faintest clues. The implications of discovering Technicolor particles would be monumental. Not only would it revolutionize our understanding of mass, but it could also open the door to new physics beyond the standard model. It might even provide insights into other cosmic mysteries, such as dark matter or the unification of forces. While the search is ongoing, the very possibility of Technicolor particles reminds us that the universe still holds countless secrets waiting to be uncovered. As we wrap up this exploration of Technicolor particles, it's clear that they represent a bold and innovative approach to one of physics' most fundamental questions. They challenge us to think beyond the familiar and consider new ways of understanding the building blocks of reality. And with that, let's turn our attention to another fascinating theory: Majorana fermions, particles that blur the line between matter and antimatter. Now, let's venture into the fascinating world of Majorana fermions, particles that defy our usual understanding of matter and antimatter. Unlike most particles, which have distinct antiparticles with opposite properties, Majorana fermions are unique because they are their own antiparticles. This peculiar characteristic makes them a subject of intense interest in both particle physics and quantum computing. To understand why Majorana fermions are so special, let's take a step back. In the standard model of particle physics, every particle has an antiparticle counterpart. For example, the electron has the positron, its antimatter twin. But Majorana fermions break this rule. They are essentially identical to their own antiparticles. This strange behavior was first proposed by the Italian physicist Majorana in the 1930s, and while they haven't been definitively observed yet, their potential existence could revolutionize our understanding of the universe. One of the most exciting applications of Majorana fermions lies in the field of quantum computing. In a quantum computer, information is stored in qubits, which are highly sensitive to external disturbances. Majorana fermions, however, have a unique property called topological protection, which makes them incredibly stable against such disturbances. This stability could pave the way for more robust and error-resistant quantum computers, bringing us closer to realizing the full potential of this groundbreaking technology. But the intrigue doesn't stop there. Majorana fermions also hold promise in the search for dark matter. Some theories suggest that dark matter could be composed of particles that are their own antiparticles, much like Majorana fermions. If this turns out to be true, it could provide a crucial link between the mysterious dark matter that permeates the universe and the particles we're familiar with. Detecting Majorana fermions could therefore shed light on one of the greatest mysteries in modern physics. So, how do scientists search for these elusive particles? One approach involves studying exotic materials such as superconductors, where Majorana fermions might emerge under specific conditions. Another method focuses on high-energy particle collisions, looking for signatures that match the predicted behavior of these particles. While the search is challenging, the potential rewards ranging from advanced quantum technologies to insights into dark matter make it a pursuit worth pursuing. As we wrap up this exploration of Majorana fermions, it's clear that these particles represent a bridge between the known and the unknown. They challenge our understanding of matter and antimatter while offering tantalizing possibilities for the future of technology and cosmology. And with that, let's turn our attention to another intriguing theory: black hole remnants and their potential role in explaining dark matter. Now, shifting our gaze to the cosmos, let's explore the intriguing possibility that black hole remnants might hold the key to unraveling the mystery of dark matter. When we think of black holes, we often imagine them as cosmic vacuum cleaners devouring everything in their path. But what happens when a black hole reaches the end of its life? According to some theories, the answer could lie in the remnants left behind: tiny, nearly invisible objects that might just be the dark matter we've been searching for. The idea stems from a process called Hawking radiation, proposed by physicist Stephen Hawking. Over incredibly long timescales, black holes are thought to slowly lose mass and energy, eventually evaporating entirely. But what remains after this evaporation? Some scientists suggest that instead of disappearing completely, black holes leave behind ultra-dense remnants, often referred to as black hole relics. These remnants could be incredibly small, perhaps even smaller than an atom, yet they would still carry the gravitational imprint of their former selves. What makes this theory so compelling is that these remnants could be virtually undetectable by conventional means. They wouldn't emit light or interact strongly with ordinary matter, making them perfect candidates for dark matter. If dark matter is indeed composed of these black hole remnants, it would explain why we've struggled to detect it directly. It's not made of particles in the traditional sense, but rather the ghostly echoes of long-dead black holes. But how do we go about searching for something so elusive? One approach involves looking for the gravitational effects these remnants might have on their surroundings. For instance, if a black hole remnant passed near a star or a galaxy, its gravitational pull could subtly distort the light from those objects, a phenomenon known as gravitational lensing. Another method focuses on the early universe, where primordial black holes, those formed in the first moments after the Big Bang, might have left behind a population of remnants that now permeate the cosmos. Of course, detecting these remnants is no easy task. Their tiny size and weak interactions make them incredibly difficult to observe directly. Additionally, the theory itself is still speculative, with many questions remaining about the exact nature of these remnants and how they fit into our broader understanding of physics. But if proven true, it would be a groundbreaking discovery, linking the enigmatic nature of black holes to the equally mysterious dark matter that shapes our universe. As we ponder the possibility of black hole remnants as dark matter, we're reminded once again of the universe's ability to surprise us. From the tiniest particles to the most massive cosmic structures, the answers to our deepest questions often lie in the most unexpected places. And with that, let's turn our attention to another fascinating theory: cue balls and their potential role in the cosmic puzzle of dark matter. Now, let's venture into the realm of cue balls, a fascinating and somewhat peculiar concept in the world of particle physics. Imagine a cosmic object that isn't quite a particle, nor a traditional form of matter, but something in between, a stable, bubble-like structure made of scalar fields. These are cue balls, and they might just hold the key to understanding dark matter. So, what exactly are cue balls? In simple terms, they are hypothetical solitons, which are stable, localized energy configurations that can exist in certain types of scalar fields. Think of them as cosmic bubbles that don't pop, maintaining their shape and energy over time. Unlike particles, which are point-like, cue balls are extended objects, and their stability comes from a conserved quantity known as Q, or charge. This charge isn't electric charge, but rather a quantum number tied to the field that forms the cue ball. One of the most intriguing aspects of cue balls is their potential connection to dark matter. Because they are stable and don't interact strongly with ordinary matter, cue balls could be floating through the universe right now, completely invisible to our detectors. If dark matter is made up of cue balls, it would explain why it's so difficult to detect these objects wouldn't emit light or interact electromagnetically, making them nearly impossible to observe directly. But how could cue balls have formed in the first place? The answer lies in the early universe. During the chaotic moments after the Big Bang, the universe was filled with scalar fields, fields that permeate space and can give rise to particles and other structures. Under certain conditions, these fields could have clumped together to form cue balls, much like droplets condensing out of a mist. These cue balls would then have persisted, surviving the expansion and cooling of the universe to become part of the cosmic landscape we see today. Detecting cue balls, however, is no small feat. Their lack of interaction with ordinary matter means they could pass through Earth without leaving a trace. But scientists have proposed some creative ways to search for them. One idea involves looking for the rare occasions when a cue ball interacts with a nucleus in a detector, producing a tiny burst of energy. Another approach focuses on the gravitational effects cue balls might have, such as distorting the light from distant stars or galaxies. While cue balls remain speculative, their potential to explain dark matter is too compelling to ignore. They represent a unique intersection of particle physics and cosmology, offering a fresh perspective on one of the universe's greatest mysteries. As we continue to explore the cosmos, who knows? The answer to dark matter might just be hiding in these enigmatic, bubble-like structures. With cue balls adding another layer to the dark matter puzzle, let's turn our attention to another cosmic mystery, cosmic strings and their potential role in shaping the universe. Now, shifting our gaze to another cosmic enigma, let's unravel the mystery of cosmic strings. These are not your everyday strings, but rather one-dimensional defects in the very fabric of space-time itself. Picture the universe as a vast, intricate tapestry. Cosmic strings would be like tiny, thread-like imperfections woven into this tapestry, remnants of the early universe's rapid expansion and cooling. So, what exactly are cosmic strings? They are theoretical structures predicted by certain models of the early universe, particularly those involving phase transitions. Imagine the universe cooling down after the Big Bang, much like water freezing into ice. Just as cracks can form in ice as it solidifies, cosmic strings could have formed as the universe transitioned into its current state. These strings are incredibly thin but unimaginably dense, with a thickness smaller than an atom, but with masses that could stretch across entire galaxies. One of the most fascinating aspects of cosmic strings is their potential connection to dark matter. While they aren't made of dark matter themselves, their gravitational effects could influence the distribution of dark matter in the universe. Cosmic strings could act as cosmic seeds, pulling matter together and helping to form the large-scale structures we see today, like galaxies and galaxy clusters. In this way, they might play a hidden but crucial role in shaping the cosmos. But how do we detect something so elusive? Cosmic strings don't emit light, but they leave behind subtle clues. One way scientists hope to find them is by looking for their gravitational effects. As cosmic strings move through space, they can create ripples in space-time, much like a stone dropped in a pond. These ripples, known as gravitational waves, could be detected by observatories like LIGO or future space-based detectors. Another signature of cosmic strings is their ability to bend light. If a cosmic string passes between us and a distant galaxy, it could distort the galaxy's image, creating a phenomenon called gravitational lensing. While cosmic strings remain theoretical, their discovery would be a monumental breakthrough in our understanding of the universe. They offer a unique window into the early moments of cosmic history and could help explain some of the most puzzling questions in physics, from the nature of dark matter to the origins of cosmic structure. As we continue to probe the universe's deepest secrets, cosmic strings remind us that even the smallest imperfections can have a profound impact on the grand tapestry of existence. With cosmic strings adding yet another layer to our exploration of the universe's hidden particles, let's now turn our attention to another intriguing possibility: hidden photons and their potential role in the cosmic puzzle. Now, let's venture into the realm of hidden photons, a fascinating yet elusive concept that could hold the key to unlocking some of the universe's deepest secrets. Hidden photons are hypothetical particles that, as the name suggests, interact very weakly with ordinary matter. Think of them as cosmic ghosts passing through the universe almost unnoticed, yet potentially shaping its very fabric in ways we're only beginning to understand. So, what exactly are hidden photons? In simple terms, they are particles similar to the photons we know, the particles of light but with a twist. While ordinary photons are the carriers of electromagnetic force and interact with charged particles like electrons, hidden photons belong to a hypothetical, hidden sector of particles. This means they don't interact with the electromagnetic force in the same way, making them incredibly difficult to detect. They're like the universe's silent observers, influencing events from the shadows. One of the most intriguing possibilities is that hidden photons could play a role in explaining dark matter. While they aren't dark matter themselves, their interactions with ordinary matter and other hidden particles could provide clues about how dark matter behaves. For instance, hidden photons might mediate forces between dark matter particles, helping to explain why dark matter clumps together in the way we observe. This could offer a new perspective on the invisible scaffolding that holds galaxies together. But how do we even begin to search for something so elusive? Scientists have proposed several clever methods to detect hidden photons. One approach involves looking for their subtle effects on ordinary photons. If hidden photons exist, they could occasionally mix with regular photons, causing tiny changes in the behavior of light. Experiments using highly sensitive instruments, like those designed to detect minute variations in electromagnetic fields, are currently underway to hunt for these faint signals. Another method involves searching for hidden photons produced in the sun or other cosmic environments, where their presence might leave behind detectable traces. The implications of discovering hidden photons would be profound. Not only could they shed light on the nature of dark matter, but they might also help us understand the fundamental forces that govern the universe. Hidden photons could even provide a bridge between the visible and hidden sectors of the cosmos, offering a glimpse into a world of particles and interactions that have so far remained beyond our reach. As we continue to explore the universe's hidden particles, hidden photons remind us that even the most subtle forces can have a significant impact. They challenge us to think beyond the familiar and to consider the possibility that the cosmos is far more complex and far more mysterious than we ever imagined. With that in mind, let's now turn our attention to another intriguing theory: the possibility that neutrinos or a heavier variant of them could account for dark matter. Now, shifting our focus to another captivating idea, let's explore the possibility that neutrinos, or perhaps a heavier version of them, could be the key to unraveling the mystery of dark matter. Neutrinos are among the most abundant particles in the universe, yet they're also some of the most elusive. These tiny, nearly massless particles zip through space at nearly the speed of light, barely interacting with matter. But could they, or a more massive cousin, be the invisible glue holding the cosmos together? To understand this theory, let's start with what we know about neutrinos. They're produced in enormous quantities by stars, supernova, and even nuclear reactions here on Earth. Despite their abundance, neutrinos are famously hard to detect because they rarely interact with other particles. They can pass through entire planets without leaving a trace, earning them the nickname ghost particles. But here's the twist: while the neutrinos we've observed so far are incredibly light, scientists have theorized the existence of heavier neutrinos, often called sterile neutrinos, which could have the right properties to explain dark matter. Sterile neutrinos are hypothetical particles that don't interact through the weak force, unlike their ordinary counterparts. This makes them even more elusive, but it also means they could be a perfect candidate for dark matter. If sterile neutrinos exist, they might have just enough mass to account for the gravitational effects we attribute to dark matter, while still being invisible to our current detection methods. This idea has sparked a lot of excitement in the scientific community, as it could provide a natural explanation for one of the universe's biggest mysteries. So, how do we go about searching for these ghostly particles? One approach involves looking for the subtle effects they might have on the universe. For example, sterile neutrinos could decay into ordinary neutrinos and photons, leaving behind faint signals that we might detect with sensitive instruments. Another method involves studying the cosmic microwave background, the afterglow of the Big Bang, for clues about how sterile neutrinos might have influenced the early universe. Experiments like the upcoming Deep Underground Neutrino Experiment, or DUNE, are also designed to probe the properties of neutrinos in unprecedented detail, potentially shedding light on whether heavier variants exist. The implications of discovering that neutrinos or sterile neutrinos are dark matter would be groundbreaking. It would not only solve one of the most pressing questions in cosmology, but also deepen our understanding of particle physics. Neutrinos are already fascinating because they challenge our understanding of mass and energy, and if they turn out to be linked to dark matter, it would open up entirely new avenues of research. As we continue to explore the universe's hidden particles, the idea of neutrino dark matter reminds us that sometimes the answers we seek are hiding in plain sight, or, in this case, zipping through it at nearly the speed of light. With that in mind, let's now turn our attention to another intriguing theory: the particles predicted by string theory and their potential to unify the forces of nature. Now, let's dive into the fascinating world of string theory and the particles it predicts. String theory is one of the most ambitious attempts to unify all the forces of nature, including gravity, into a single framework. At its core, string theory suggests that the fundamental building blocks of the universe aren't point-like particles, as we traditionally think of them, but tiny, vibrating strings. These strings can oscillate in different ways, and each unique vibration corresponds to a different particle. This means that everything in the universe, from the smallest quark to the largest galaxy, could be made up of these incredibly small strings. One of the most exciting aspects of string theory is that it predicts the existence of a vast array of particles, many of which we haven't yet observed. Some of these particles could be the hidden particles we've been searching for, including potential candidates for dark matter. For example, string theory introduces the idea of supersymmetry, which proposes that every known particle has a heavier superpartner. These superpartners could include particles like neutralinos, which we've already discussed as potential dark matter candidates. But string theory goes even further, suggesting the existence of entirely new classes of particles that could interact in ways we've never imagined. What makes string theory particularly compelling is its potential to unify physics. Right now, we have two major frameworks that describe the universe: quantum mechanics, which explains the behavior of particles on the smallest scales, and general relativity, which describes gravity and the large-scale structure of the cosmos. These two theories don't always play nicely together, especially when it comes to extreme environments like black holes or the early universe. String theory aims to bridge this gap by providing a single, elegant framework that can explain both the quantum world and the force of gravity. But how does this connect to dark matter? Well, some of the particles predicted by string theory could have just the right properties to account for the invisible matter that shapes the universe. For instance, certain string theory models predict the existence of particles that interact only weakly with ordinary matter, making them nearly impossible to detect with current technology. These particles could be floating through space right now, exerting gravitational effects without us even realizing it. If string theory is correct, it could provide a natural explanation for dark matter while also solving some of the biggest puzzles in physics. Of course, string theory is still a work in progress, and many of its predictions remain untested. detecting the particles it predicts would require experiments far beyond our current capabilities. But the potential rewards are enormous. If string theory is proven correct, it wouldn't just explain dark matter. It would revolutionize our understanding of the universe, revealing a deeper, more unified reality than we've ever imagined. As we continue to explore the mysteries of the cosmos, string theory reminds us that sometimes the answers lie in the most unexpected places, like the vibrations of unimaginably tiny strings. With that in mind, let's turn our attention to the final theory in our list: exotic hadrons and their potential role in the universe's hidden particles. Now, shifting our focus to the final theory in our exploration, let's delve into the intriguing world of exotic hadrons. Unlike the familiar protons and neutrons that make up the nucleus of an atom, exotic hadrons are particles that go beyond the standard model of particle physics. These particles are not made up of the usual combinations of quarks we're accustomed to. Instead, they represent entirely new configurations, some of which include additional quarks or even gluons, the particles that mediate the strong force holding quarks together. One of the most fascinating aspects of exotic hadrons is their potential connection to dark matter. While the standard model has been incredibly successful in explaining the particles and forces we observe, it doesn't account for dark matter. Exotic hadrons, however, could offer a solution. Some theories suggest that these particles might have properties that make them invisible to our current detection methods, yet still capable of exerting gravitational influence. This means they could be hiding in plain sight, contributing to the mysterious dark matter that shapes the cosmos. Detecting exotic hadrons is no small feat, but particle colliders like the Large Hadron Collider are at the forefront of this search. By smashing particles together at incredibly high energies, scientists hope to create and observe these elusive particles. While no definitive evidence has been found yet, the discovery of exotic hadrons would not only expand our understanding of particle physics, but could also provide a crucial piece of the dark matter puzzle. What makes this search so exciting is the possibility of uncovering entirely new physics. Exotic hadrons could reveal interactions and forces that we've never seen before, opening up a whole new realm of exploration. They might even help us understand why the universe is made up of matter rather than antimatter, one of the biggest unanswered questions in science. As we wrap up our journey through these 30 theories, it's clear that the universe is far more complex and mysterious than we often realize. From the tiniest strings predicted by string theory to the potential existence of exotic hadrons, each idea offers a glimpse into the hidden layers of reality. While many of these theories remain unproven, they remind us of the boundless curiosity and ingenuity driving humanity's quest to understand the cosmos. And who knows, the next groundbreaking discovery could be just around the corner, waiting to reshape our understanding of the universe once again. As we bring this cosmic journey to a close, let's take a moment to reflect on the incredible theories we've explored. From the elusive nature of dark matter and dark energy to the mind-bending possibilities of extra dimensions and quantum foam, each theory offers a unique lens through which we can glimpse the hidden workings of the universe. We've ventured into the realm of hypothetical particles like Axions, WIMP, and Gravitons, and pondered the mysteries of supersymmetry, primordial black holes, and even faster-than-light tachyons. These ideas, while still unproven, remind us of the vastness of what we don't yet know, and the thrilling potential for discovery that lies ahead. What ties all these theories together is their shared goal: to uncover the secrets of the cosmos. Whether it's explaining the invisible forces shaping galaxies or probing the tiniest building blocks of reality, each theory pushes the boundaries of human understanding. They challenge us to think bigger, dig deeper, and question everything we thought we knew. And while many of these ideas remain speculative, they serve as stepping stones, guiding scientists toward new experiments, technologies, and breakthroughs that could one day revolutionize our view of the universe. But the journey doesn't end here. The universe is full of mysteries waiting to be unraveled, and every discovery brings us closer to understanding our place in the grand cosmic tapestry. So, what do you think? Which of these theories fascinates you the most? Do you believe we're on the verge of a major breakthrough, or is there a hidden particle or force out there that we haven't even imagined yet? Share your thoughts in the comments below. We'd love to hear your ideas and theories. If you enjoyed this deep dive into the universe's hidden particles, don't forget to hit the like button and subscribe to the channel for more mind-blowing explorations of space, science, and the mysteries that surround us. And as always, keep looking up because the universe is full of wonders just waiting to be discovered. Until next time, stay curious.